Okay, so we're going to be going over what insertion sort is, and how it works. So, what exactly is it? Well, it's a sorting algorithm. Right, algorithm. I hope that's right. Um, you start from the left of the array and work your way to the right, and you examine the value at each index of the array. And you compare the current element to the element prior, or the element to the left of it. And based on that comparison, you perform a swap to the left until the element prior to the current element is less than it. And you keep doing that until the whole array is sorted. Okay, so let's do a little demonstration of this. So let's say you have an array with 59, 11, 21, 58, 52, 52, and 3. Okay, so we first start at 59, our first element in the array. There's nothing behind it, so uh, it's in its correct position already, so it can stay there. So we move to the next element at the next index, 11. Now, 11 is less than 59, so we need to move it right, or left, pardon me. We need to move it one space this way. Okay, and now 11 is in its correct position, so we move to the next index, 21. 21 is also less than 59, so we move it one space. However, it is greater than 11. So it will just only have to move one spot. And we move on to the next index. So this section so far is correctly sorted. Now all we have to worry about are these three elements in the array. So we're at 58. 58 is less than 59, so we move it one position over. And that's where we stop because it's greater than 21. So we have now we can check out 52. 52 is less than 59, so we move it to the left one. we make another comparison. 52 is less than 58. Move it over one more. So now we have our new array. And there's just one more comparison left. We're at the last index. So 3 is less than 59, less than 58, less than 52, less than 21, less than, you guessed it, 11. So finally, we have our new array, our new sorted array. All nice and sorted. And notice with each turn, all these elements to the left of the current element, they're all nice and sorted in numerical order. So let me show you the pseudocode for this. This is Insertion Sort, the code for this. I think I called this pseudocode. This is the code, my bad. So there's two important functions in this, two important methods. So first we have the insertion sort method. These are both recursive, by the way. So with insertion sort, it takes the array of integers that need to be sorted and the last index of the array. And insertion sort is recursively called until the array is broken down into smaller and smaller subarrays. And these will be guaranteed to be sorted. And then after that, swap left is called, and the element at the current index is called end here, at index end. It will be swapped into the correct position leftwards until it's in the correct numerical order, until the element to the left of it is less than it, or yeah. And this insertion sort is you leave the method once you arrive at the start of the array. That means there's no more sorting that you can do. And this is swap left. This is the method that does the actual swapping of elements. So this is just the swapping itself. And then you recursively call the function again and again and again to do another swap and another swap and another swap until the current element arrives at its correct position. And you know it's at its correct position once you reach the exit condition. So you leave the method if you arrive at the first element or the first index of the array, or the current element has a value that's greater than the element at the index before it. So this means that it's at the correct spot in its array. So one last thing is the time complexity. So with this, we'll start with the worst case scenario. Worst case. So this is the array is sorted. Hooray! But it's sorted backwards. So you see how these elements up here, insertion sort sorted them from lowest to highest? Well, this would be an array that's sorted from highest to lowest. So um, every value must be shifted through the sorted part of the array. So the moves insertion sort would have to perform would be like this. So at the first value, it doesn't have to make a shift. At the second value, one shift has to be made. At the third value, the third index, two shifts have to be made for it to be in its correct spot. And this keeps going on and on and on. And this pattern can be described numerically like this. And this is the total number of operations for n elements in an array. This can be rewritten as an arithmetic series. So n times n minus 1 over 2. This is an arithmetic series. And this series can be expanded to this. I just distributed the n. Now, for a big O notation of time complexity, you want to focus on the term that's the most dominant. And so the n squared term is the most dominant, like this 1/2 really doesn't do anything. Subtracting n over a half doesn't really do anything to it. So therefore, the time complexity of this is big O of n squared for the worst case. And for the average case, the time complexity is also O of n squared. The average case is just, you'll have to do a varied amount of comparisons depending on the positions of all the numbers in the array. But the math works out so that n squared is still the dominant term, so the time complexity is still big O of n squared. And finally, for the best case scenario for time complexity. So the best case for this sorting is the array is sorted correctly. From low to highest value. So the insertion sort only needs to make a comparison it only needs to compare the element before the current element it's as the index of to confirm that yes, that element is at the right index. And this depends on the array length. So n elements in the array. This is the array length determines the number of comparisons it makes. So that is a linear time complexity. And a linear time complexity that is big O of n. And that's about it for insertion sort. Thank you.